Right now, beneath our solar system, something extraordinary exists that most people never consider. When you think about space, you probably imagine planets, stars, maybe the occasional asteroid. But what if I told you there's an entire cosmic architecture stretching below us that shapes everything about our place in the universe? Here's the thing about below in space. It's not as simple as down on Earth. There's no universal up or down in the cosmos, but scientists have established reference frames that let us map what exists in different directions from our solar system. And when we look in the direction we call below, we're actually peering through layers of cosmic structure that reveal how our little corner of space fits into the galactic neighborhood. The solar system sits tilted at about 60 degrees relative to the plane of our galaxy. Picture a dinner plate representing the Milky Way's disk, and then imagine our solar system as a smaller plate sitting at a steep angle on top of it. We're not aligned with the galactic plane. We're sailing through space almost sideways, like a ship cutting across ocean currents rather than riding with them. This 60-degree tilt means that when we look below our solar system's ecliptic plane, we're not looking straight down through the galaxy's disk. We're looking at a complex angle that takes us through multiple cosmic structures. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Currently, our solar system is positioned about 55 light-years above the galactic plane, and we're moving northward, away from it, at roughly 7 kilometers per second. Think about that for a moment. We're not stationary. We're climbing higher above the galactic disk even as we orbit around its center. This movement means that below us lies the direction back toward the galactic plane, and beyond it to the southern galactic hemisphere. But before we even leave our immediate neighborhood, there's something surrounding us in all directions, the Oort Cloud. Unlike the flat disk of planets and asteroids we're familiar with, the Oort Cloud forms a massive sphere around our entire solar system. It stretches from roughly 2,000 astronomical units from the Sun, all the way out to potentially 200,000 astronomical units. That's nearly a third of the distance to the nearest star. This isn't a dense collection of objects. It's a sparse shell of icy bodies, remnants from the solar system's formation that got kicked out to these extreme distances by gravitational interactions with the giant planets billions of years ago. These chunks of ice and rock don't orbit in neat, orderly paths like the planets. They travel at all angles, swooping under, over, and around the Sun in chaotic trajectories. When gravity occasionally nudges one of these icy wanderers toward the inner solar system, we see it as a long-period comet, visitors from the deep freeze at the solar system's edge. The Oort Cloud exists equally below our ecliptic plane as it does above it. So the moment we start looking down from the solar system, we're already looking through this vast spherical shell of frozen objects. It's our solar system's outermost boundary, the last remnant of the Sun's gravitational influence before interstellar space truly begins. Speaking of that boundary, there's another structure that wraps around us completely. The heliosphere. The Sun doesn't just sit quietly in space, radiating light and heat. It blasts out a continuous stream of charged particles called the solar wind, traveling at hundreds of kilometers per second in all directions. This wind creates a bubble a protective cocoon that shields our solar system from the harsher radiation and cosmic rays of interstellar space. The heliosphere extends roughly 11 billion miles from the Sun before the solar wind finally runs out of energy and gives way to the interstellar medium. That boundary, called the heliopause, exists below our solar system just as it does above. Voyager 2, after its flyby of Neptune, was deflected downward and is currently traveling below the plane of the planets, exploring the heliosphere's structure in that direction as it journeys into interstellar space. The heliosphere isn't perfectly spherical. It's more like a comet, with a rounded front facing the direction of our motion through the galaxy and a long tail streaming behind us. But in all directions, including below, it marks where our Sun's influence ends and true interstellar space begins. Once we cross that boundary, we enter something called the Local Interstellar Cloud. This might sound like just empty space with a fancy name, but it's actually a distinct region of the interstellar medium with its own characteristics. The Local Interstellar Cloud has about 0.3 atoms per cubic centimeter. That sounds incredibly sparse, and it is. It's still a better vacuum than anything we can create on Earth, but it's actually 6 times denser than the even more rarefied region surrounding it. What's fascinating is that this cloud has a temperature of about 7,000 Kelvin. That's roughly the same temperature as the surface of the Sun. You might wonder why we don't feel this heat, but temperature and heat are different things when you're dealing with such sparse material. There are so few particles that despite their high speed, which we measure as temperature, there's almost no thermal energy to transfer. It's like the difference between a single spark and a bonfire. The spark might be hotter, but the bonfire contains vastly more heat. Our solar system entered this cloud relatively recently, probably within the last 100,000 years or so. We're currently positioned near one edge of it, about 0.3 parsecs from its boundary. As we continue moving northward away from the galactic plane, we'll eventually exit this cloud and enter whatever lies beyond. The Local Interstellar Cloud itself sits within something much larger, the local bubble. This is where the cosmic architecture starts to reveal its true scale. The local bubble is a region of space at least 1,000 light-years across, carved out by supernova explosions that occurred 10 to 20 million years ago. More than a dozen massive stars exploded in this region, blasting away the normal interstellar gas and creating a vast cavity of hot, extremely low-density material. We happened to enter this bubble about 5 million years ago as our solar system orbits around the galactic center. Pure coincidence placed us near the center of this enormous void. The local bubble isn't perfectly spherical. Recent observations suggest it's more like an hourglass or tube shape, narrower in the galactic plane and widening above and below it. This means the bubble extends more prominently in the directions perpendicular to the galactic disk, including below our solar system. The density inside the local bubble is incredibly low, about 0.05 atoms per cubic centimeter. That's 16 times less dense than the average interstellar medium. Nearly every star-forming cloud of gas and dust near our Sun lies at the edge of this bubble, where material has been compressed by the expanding blast waves from those ancient supernovae. The bubble is still expanding today, slowly growing as it pushes against the surrounding interstellar medium. But here's where it gets even more intriguing. The local bubble isn't isolated. Recent research has uncovered what appear to be tunnels, channels of hot, low-density plasma that connect our bubble to other cavities in the interstellar medium. One tunnel seems to stretch toward the constellation Centaurus. Another appears to link toward Canis Major. These interconnecting passages were created when multiple supernova-blown bubbles encountered each other and merged, forming pathways through the denser surrounding gas. These tunnels extend in multiple directions, and some likely reach into the region below our solar system's plane. Think of the structure like a sponge, with the holes representing the low-density bubbles and tunnels, and the sponge material representing the denser, normal interstellar medium. Our solar system happens to be floating through one of these holes, with pathways leading to other holes in various directions. All of this, the local interstellar cloud and the local bubble, exists within an even larger structure, the Orion Arm, also called the Orion Spur. This is a minor spiral arm of the Milky Way galaxy, spanning about 3,500 light-years in width and extending roughly 20,000 light-years in length. Our solar system sits near the inner rim of this arm, about halfway along its length. The Orion Arm isn't one of the major spiral arms of the galaxy. It's more like a bridge or spur connecting the larger Sagittarius and Perseus arms. But it's still a massive structure containing billions of stars, including most of the bright stars we see in our night sky. The arm exists as a three-dimensional structure that extends both above and below the galactic plane, though we're currently positioned above that plane as we travel through it. Understanding our position within the Orion Arm helps explain what we see when we look in different directions. Looking below our solar system, we're looking toward the galactic plane and eventually through it to the opposite side. Since we're 55 light-years above the plane and moving away from it, the direction we call below takes us back toward that plane and into the southern galactic hemisphere. But our motion through the galaxy isn't just a simple orbit around the center. The solar system oscillates up and down through the galactic plane like a wave. The complete oscillation takes about 70 million years, meaning we cross through the plane every 35 million years. We last crossed it roughly 3 million years ago and won't do so again for another 30 million years. This oscillating motion happens because of gravity. All the matter in the galactic disk pulls on us, creating a gravitational force perpendicular to the plane. When we're above the plane, that force pulls us downward. We accelerate toward the plane, pass through it, and overshoot to the other side. Then the force reverses, pulling us back toward the plane again. It's like a weight bouncing on a spring, constantly oscillating around an equilibrium point. Currently moving northward, away from the plane, we're in the upward phase of this oscillation. Eventually, gravity will slow our northward motion, stop it, and reverse it, sending us back down through the plane. This cosmic dance has been happening for the entire history of our solar system, carrying us through different regions of the galaxy and exposing us to different densities of interstellar material and cosmic rays. The direction we call below our solar system takes us toward a specific region of the sky. The South Galactic Pole, the point directly perpendicular to the galactic disk, lies in the constellation Sculptor. When we look towards Sculptor, we're looking through our galaxy's south window, peering away from the dense concentration of stars in the galactic plane. This is why Sculptor contains very few bright stars. We're looking perpendicular to where most stars are concentrated. This relatively clear view makes the South Galactic Pole direction ideal for observing beyond our own galaxy. Looking toward the poles, We're not looking through the dust, gas, and billions of stars that fill the galactic disk. We're looking more directly into intergalactic space, where we can observe distant galaxies and cosmic structures with less interference from our own galaxy's material. And that's where the story really opens up. Because below our solar system, beyond the Oort Cloud, past the heliopause, through the Local Interstellar Cloud and the local bubble, beyond even the Orion Arm and the Milky Way itself, lie structures that dwarf everything we've discussed so far. The local group stretches 17 million light-years across, containing at least 134 galaxies that we know of. The Milky Way forms one lobe of this dumbbell-shaped structure, while Andromeda and its satellites form the other. Between them lies a gravitational dance that's been pulling these two massive galaxies toward each other for billions of years. They're approaching at roughly 75 miles per second. In about 4 billion years, they'll collide. Not a destructive crash, but a slow gravitational merger that will reshape both galaxies into something new. Stars will rarely collide because the distances between them are so vast, but the galaxies themselves will pass through each other, twist, distort, and eventually settle into a single elliptical galaxy. Future astronomers, if they exist, will inhabit a very different cosmic neighborhood than we do. But the local group doesn't float alone in space. It's embedded in something larger, the local sheet. This isn't a galaxy cluster, but a flat arrangement of galaxies stretching across space like a cosmic pancake. The sheet extends for tens of millions of light years, and its flatness isn't random. It's been shaped by gravity and the distribution of matter across cosmic time. What makes the local sheet particularly interesting is what it borders. On one side lies normal cosmic structure, more galaxies and matter distributed in the typical cosmic web pattern. On the other side lies something very different. The local void, discovered in 1987 by astronomers Brent Tully and Rick Fisher. The local void is exactly what it sounds like. An enormous region of space with far fewer galaxies than average. It stretches at least 150 million light-years across, possibly much larger. The void isn't completely empty, but its galaxy density is dramatically lower than surrounding regions. The precise shape and extent of the local void remains somewhat mysterious even after decades of study. Recent mapping has revealed it's actually composed of 3 separate sectors connected by thin filaments of matter. These filaments are like bridges spanning an otherwise empty expanse, containing just enough galaxies to prove the void isn't absolute nothingness, but rather a profound underdensity. The local void sits adjacent to our local group. Depending on its exact 3-dimensional orientation, portions of it extend in the direction we consider below our solar system. When you look towards certain southern constellations, you're looking toward, or perhaps even into, this vast cosmic emptiness. Voids like this are common in the universe's large-scale structure. The cosmic web consists of filaments dense with galaxies, nodes where filaments intersect containing galaxy clusters, sheets where matter spreads in 2 dimensions, and voids where matter is scarce. The voids aren't failures of structure formation, but natural consequences of how gravity works on cosmic scales. Matter clumps together along filaments and sheets, leaving vast regions relatively empty. But there might be something even larger. Something that would make the local void seem modest by comparison. Some researchers propose we're living inside what's called the KBC Void, or local hole. Named after astronomers Ryan Keenan, Amy Barger, and Laniakea, who studied it in 2013, this structure would be immense, roughly 2 billion light-years across, 20% less dense than the average universe. If it exists, the KBC Void would contain the Milky Way, the entire local group, most of the Laniakea Supercluster, and the local void itself. Everything we consider our cosmic neighborhood would be nested inside this larger underdensity, like Russian dolls of increasingly vast emptiness. The evidence for the KBC Void comes from observations of cosmic expansion. When astronomers measure how fast the universe is expanding using nearby galaxies, they get one answer. When they measure expansion using the cosmic microwave background radiation from the early universe, they get a slightly different answer. This discrepancy is called the Hubble tension, and it's been bothering cosmologists for years. One possible explanation is that we're in a void. If our local region has lower than average density, the expansion rate we measure nearby would differ from the average expansion rate across the entire universe. We'd be living in an atypical region that skews our measurements. Recent research using baryon acoustic oscillations, sometimes called the sound of the Big Bang, suggests this void model might be valid. These oscillations are ripples in matter density left over from the early universe, and their scale gives us a cosmic ruler for measuring distances and densities. The measurements seem to support the idea that we're in a local underdensity, but not all astronomers are convinced. The evidence remains debated. If the KBC Void exists, it would surround us in all directions, including below the solar system. Every direction you look would be looking through this vast region of lower than average cosmic density. Whether or not we're in a supervoid, we're definitely surrounded by the dark matter halo of our galaxy. This invisible mass distribution extends far beyond the visible disk of the Milky Way, reaching out at least 300,000 light-years from the galactic center, possibly further. The dark matter halo is roughly spherical, meaning it extends equally in all directions. When you look below the solar system, you're looking through dark matter. When you look up, left, right, anywhere, you're looking through it. This invisible scaffolding outweighs the Milky Way's visible matter by a factor of 20. 95% of our galaxy's mass is dark matter that we can only detect through its gravitational effects. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all as far as we can tell. It only reveals itself through gravity. Galaxies rotate too fast to be held together by their visible matter alone. Galaxy clusters contain more gravitational mass than their galaxies can account for. Gravitational lensing bends light around invisible mass concentrations. All of this points to dark matter's existence, but we still don't know what it's made of. The halo extends far beyond the Milky Way's visible structure, creating an enormous sphere of gravitational influence. Satellite galaxies orbit within this halo. The Magellanic Clouds, small and large, are being drawn through it. Distant stars far from the galactic disk are held in place by it. The halo is the galaxy's true boundary, the region where the Milky Way's gravity dominates over intergalactic space. But even this vast dark matter distribution is just one structure in a hierarchy that keeps expanding. The local group is part of the Laniakea Supercluster, discovered in 2014. Laniakea is Hawaiian for immense heaven, and the name fits. This supercluster contains roughly 100,000 galaxies spread across 520 million light-years. Laniakea's galaxies aren't randomly distributed. They flow along filaments toward a central basin of attraction called the Great Attractor. This gravitational anomaly pulls galaxies from across the supercluster, including our own. The Milky Way is moving toward the Great Attractor at approximately 1,400,000 miles per hour, carried along by the supercluster's internal dynamics. The Great Attractor itself lies in the direction of the Centaurus and Hydra constellations. From our perspective, it's partially obscured by the Milky Way's disk, making it difficult to observe directly. We know it's there primarily through its gravitational influence on surrounding galaxies. But the Great Attractor isn't the end of the story. It's being pulled by something even larger. The Shapley Supercluster lies beyond Laniakea, an even more massive concentration of galaxies that exerts gravitational pull across hundreds of millions of light years. The cosmic web keeps revealing larger structures, each influencing the motion of smaller structures nested within it. These vast structures exist in 3 dimensions around us. Some extend in directions we consider below the solar system. When astronomers map galaxy distributions across the entire sky, they find filaments, walls, and voids distributed in complex 3-dimensional patterns. The universe's large-scale structure resembles foam or sponge, with matter concentrated along surfaces and filaments, while voids occupy the volume between them. The Sloan Great Wall, discovered in 2003, stretches 1.3 billion light-years across. The Hercules Corona Borealis Great Wall, found in 2013, might be even larger, possibly 10 billion light-years long. These structures challenge our understanding of cosmology because they're so vast that they approach the limits of what current theory predicts should be possible. And threading through all of this, through the voids and the filaments, the dark matter halos and the galactic superclusters, runs the interstellar medium, the stuff between the stars, hydrogen and helium mostly, left over from the Big Bang, heavier elements forged in stars and scattered by supernovae, dust grains, complex molecules, cosmic rays, magnetic fields. The density varies enormously. The local bubble where we live contains only about 0.05 atoms per cubic centimeter. The local interstellar cloud is denser, about 0.3 atoms per cubic centimeter. The average interstellar medium in the Milky Way's disk contains about 0.5 atoms per cubic centimeter. These sound like trivial differences, but they matter enormously over interstellar distances. Even the densest interstellar clouds are still vacuum by Earth standards. The best laboratory vacuum chambers on Earth are far denser than most of interstellar space. But accumulated over light years, this sparse material adds up. It absorbs and scatters light, particularly blue wavelengths, causing interstellar reddening. It provides raw material for new star formation. It carries magnetic fields that thread through the galaxy. It's the medium through which shock waves from supernovae propagate. Below the solar system, this medium extends in all directions, filling the spaces between structures, connecting everything in a tenuous web of matter and energy. The interstellar medium isn't uniform, but varies with location. Hot bubbles carved by supernovae, cold molecular clouds where stars are forming, warm neutral regions, hot ionized gas, each with different temperatures, densities, and properties. Threading through the interstellar medium are magnetic fields. These fields aren't strong by laboratory standards, but extend across vast distances, creating large-scale structure in the galaxy's magnetic environment. The fields influence cosmic ray propagation, affect star formation, and create the complex environment through which the solar system moves. Recent observations suggest the local bubble might be connected to other bubbles through tunnels of hot, low-density plasma. One apparent channel stretches toward Centaurus. Another seems to link toward Canis Major. These tunnels formed where expanding supernova bubbles met and merged, creating pathways through the denser interstellar medium. If these tunnels exist, they represent large-scale structure in the local interstellar environment, channels of easier passage for cosmic rays and hot gas, regions where the properties of space differ from surrounding areas. The tunnels might extend in multiple directions, potentially including paths that reach below the solar system's ecliptic plane. All of this, the bubbles and tunnels, the dark matter halo, the local void, the possible KBC supervoid, the galactic structure, the cosmic web, exists around us in 3 dimensions. Below the solar system isn't a special direction. It's just one way of looking through this vast hierarchy of structures. But it's a direction that takes us through relatively clear space, perpendicular to the galactic disk, offering views toward intergalactic space and beyond. And beyond the structures we can see, beyond even the dark matter we can detect gravitationally, lies something else. Something that makes up most of the universe, but remains even more mysterious than dark matter. Dark energy. If dark matter is puzzling, dark energy is downright mystifying. We discovered it by accident in 1998 when 2 teams of astronomers were studying distant supernovae, trying to measure how much the universe's expansion had slowed since the Big Bang. Gravity from all the matter in the universe, both ordinary and dark, should be gradually decelerating that expansion. The question was by how much? The answer shocked everyone. The expansion wasn't slowing down, it was speeding up. This made no sense. Gravity attracts. It pulls things together. There's no known force that pushes space apart, making distant galaxies accelerate away from each other. Yet that's exactly what observations showed. Something was counteracting gravity on the largest scales, driving an accelerating expansion that seemed to violate everything we thought we knew about how the universe works. Scientists named this mysterious influence dark energy. Not because we understand what it is, but because we needed to call it something. Dark energy now appears to make up roughly 68% of the total energy content of the universe. Combined with dark matter's 27%, that means 95% of the universe consists of things we can't see and don't understand. Ordinary matter, everything we've ever touched or observed directly, accounts for just 5%. You, me, Earth, the Sun, all the stars and galaxies we can observe, everything made of atoms, represents a tiny minority of what exists. We're living in a universe dominated by invisible, poorly understood components, whose nature remains one of science's deepest mysteries. So what is dark energy? Nobody knows. We have theories, educated guesses, mathematical frameworks that might explain it, but no definitive answer. The simplest explanation involves something called the cosmological constant, a term Einstein added to his equations of general relativity, then later removed. Einstein introduced the constant to keep the universe static, matching the prevailing belief of his time that the cosmos neither expanded nor contracted. When observations proved the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder, but the concept never quite went away. In modern cosmology, the cosmological constant represents a constant energy density filling all of space. This energy doesn't dilute as the universe expands. Instead, it maintains the same density everywhere, always, creating a kind of anti-gravity that pushes space apart. The mathematics work beautifully. Insert the right value for the cosmological constant into Einstein's equations, and you get an accelerating expansion matching observations. Problem solved, right? Not exactly. Because when physicists try to calculate what that energy density should be based on quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's one followed by 120 zeros. It's the worst prediction in the history of physics. A discrepancy so enormous, it defies comprehension. Something is clearly missing from our understanding. Either quantum field theory is wrong about vacuum energy, or general relativity breaks down on cosmic scales, or there's some unknown mechanism that cancels out most of the vacuum energy, or dark energy isn't the cosmological constant at all, but something else entirely. Something dynamic that changes over time, or varies from place to place. Some theories propose that dark energy is a new type of energy field permeating space, similar to other fields in physics, but with unique properties. Others suggest modifications to general relativity that alter how gravity works on the largest scales. Still others invoke extra dimensions or quantum effects we don't yet understand. All remain speculative. What we do know is that dark energy affects everything. Below the solar system, throughout the galaxy, across the local group and Laniakea Supercluster, in the voids, and along the filaments of the cosmic web, dark energy is pushing space apart. Its influence grows stronger over cosmic distances. Within our solar system or even our galaxy, gravity dominates, and dark energy's effect is negligible. But on scales of millions or billions of light years, dark energy becomes the controlling force, driving the accelerating expansion that will determine the ultimate fate of the cosmos. Current observations suggest dark energy's density remains constant as space expands. If that continues, the universe will expand forever, accelerating without limit. Galaxies beyond our local group will eventually recede faster than light can travel, disappearing beyond a cosmic horizon we can never cross. The universe will grow darker, emptier, colder. Stars will exhaust their fuel. Black holes will evaporate. Eventually, in trillions upon trillions of years, the cosmos will approach a state of maximum entropy, a heat death where nothing interesting can happen anymore. That's one scenario, but we can't be certain dark energy will remain constant. If its density increases over time, the acceleration could strengthen, eventually tearing apart galaxies, then solar systems, then planets, then atoms themselves in a catastrophic end called the Big Rip. If dark energy somehow decreases or reverses, the expansion could slow or even reverse, leading to a big crunch where the universe collapses back on itself. We don't know which future awaits us because we don't understand what dark energy is, and that brings us back to what lies below the solar system. In every direction we look, through all the structures we've explored, the local interstellar cloud, the local bubble, the Orion Arm, the Milky Way's dark matter halo, the local void, the cosmic web, dark energy is there, invisible but dominant, shaping the large-scale structure and evolution of everything. The space below our solar system contains the same dark energy as the space above, beside, or in any other direction. It's woven into the fabric of space-time itself, an intrinsic property of empty space that we're only beginning to recognize. When we map the universe's structure, we're really mapping the interplay between three components: ordinary matter that clumps under gravity to form stars and galaxies, dark matter that provides additional gravitational scaffolding, and dark energy that pushes against that scaffolding, driving expansion and preventing structure formation on the very largest scales. This three-way competition determines everything about how the universe looks and evolves. In the early universe, matter dominated. Gravity pulled things together, forming the first stars and galaxies. As the universe expanded and matter density decreased, dark energy's influence grew. Billions of years from now, dark energy will dominate completely, unless something changes that we can't predict. The mystery extends beyond cosmology. Dark energy connects to fundamental questions about quantum mechanics, the nature of space-time, the possible existence of extra dimensions, even the arrow of time. Some theories suggest dark energy is related to the quantum vacuum, to virtual particles constantly appearing and disappearing in empty space. Others propose connections to string theory or quantum gravity. None have been confirmed. What makes dark energy particularly frustrating is that we can measure its effects with increasing precision, but those measurements don't point clearly toward any particular explanation. We know how much dark energy there is. We can track how it influences cosmic expansion. We can map its effects on the large-scale structure of the universe, but we still can't say what it actually is. This represents a profound gap in human knowledge. We've built civilization on understanding matter and energy, on harnessing natural forces, on predicting how things work based on physical laws. Yet the dominant component of the universe remains completely mysterious. It's as if we've been studying a painting while ignoring the canvas it's painted on, or analyzing a symphony while missing the concert hall's acoustics. The search for answers continues. Telescopes map the cosmos with ever greater precision, measuring the expansion rate at different distances and times. Particle accelerators probe the quantum vacuum, looking for clues about vacuum energy. Theorists develop new mathematical frameworks that might explain dark energy's properties. Satellite missions measure subtle effects that could distinguish between competing theories. But progress is slow. Dark energy doesn't interact with matter or light except through its gravitational effects. We can't capture it, examine it, or experiment with it directly. We're like detectives investigating a crime where the perpetrator is invisible and leaves no fingerprints, only subtle disturbances in the environment that require sophisticated analysis to interpret. Meanwhile, below the solar system and in every other direction, dark energy continues its work. Space expands. Distant galaxies accelerate away. The cosmic web stretches. The universe grows larger and emptier, and we watch, measure, theorize, trying to understand the invisible force reshaping everything on the grandest scales imaginable. The story of what lies below the solar system is ultimately a story about hierarchy and mystery. We start with familiar structures, the Oort Cloud, the Heliosphere, things we can at least conceptualize. Then we move to larger scales, the Local Interstellar Cloud, the local bubble, structures mapped through careful observation. Further out, we encounter dark matter, halos and voids, and the cosmic web. phenomena we detect through gravitational effects, even though we can't see them directly. And underlying everything, permeating all of space, including the space below our solar system, is dark energy, the biggest mystery of all. The force we discovered accidentally, can measure precisely, but cannot explain. The dominant component of reality that remains invisible and incomprehensible, shaping the fate of the universe through mechanisms we don't understand. That's what exists below the solar system. Not a simple answer, but layers of structure, each more mysterious than the last, culminating in a fundamental force that challenges our understanding of physics itself. And as our knowledge grows, as our instruments improve and our theories develop, we may finally begin to glimpse what dark energy actually is. Or maybe we won't. Because here's something that makes dark energy even stranger than it first appears. We've talked about this mysterious force as if it's a single, unchanging thing. But what if it isn't? What if dark energy is evolving, changing its properties as the universe ages? Some theoretical models suggest dark energy might not be constant. It could be getting stronger, growing more powerful as space expands. This scenario leads to something cosmologists call phantom energy, and the implications are genuinely unsettling. In a phantom energy universe, dark energy doesn't just accelerate expansion, it accelerates the acceleration itself. The universe doesn't just grow faster, it grows faster at an increasing rate. And this creates a countdown to cosmic catastrophe. First, galaxy clusters would be torn apart. Then individual galaxies would shred. Solar systems would disintegrate. Eventually, even atoms themselves would be ripped to pieces as space expanded faster than the forces holding matter together could compensate. This is called the Big Rip. And if phantom energy is real, it could happen in as little as 22 billion years. 22 billion years sounds distant, but consider that the universe is currently 13.8 billion years old. We'd be more than halfway to the end of everything that can exist. Other models suggest dark energy might weaken over time, or even reverse. Perhaps billions of years from now, dark energy will fade, gravity will reassert dominance, and the universe will stop expanding. Then contraction begins, leading eventually to a big crunch where everything collapses back into a singularity. Or maybe dark energy is perfectly constant, exactly as current observations suggest. In that case, the universe simply continues expanding forever, cooling and diluting until only isolated particles drift through an incomprehensibly vast void. The Big Freeze. We don't know which scenario is correct. We can't predict the ultimate fate of existence because we don't understand the force that will determine that fate. And this brings us back to the question of what lies below the solar system, because the answer depends entirely on scale and time. Right now, below our solar system, there's the Oort Cloud, the Heliosphere, the Local Interstellar Cloud, the Local Bubble, dark matter halos, the cosmic web, dark energy pervading all of it. But billions of years from now, if dark energy continues its work, what will be below the solar system? Assuming the solar system still exists, assuming the sun hasn't exhausted its fuel and become a white dwarf, assuming Earth hasn't been engulfed or ejected, what will future astronomers observe when they look in that direction? They might see nothing. By then, most galaxies will have receded beyond the cosmic horizon. The Andromeda Galaxy, currently rushing toward us and destined to merge with the Milky Way in a few billion years, will have long since completed that merger. The resulting elliptical galaxy will be one of the few large structures remaining visible. Everything else will have disappeared over the edge of the observable universe, carried away by expanding space faster than light can travel. Future civilizations, if they exist, won't be able to see the cosmic microwave background. They won't detect the large-scale structure of the universe. They won't have evidence that the Big Bang ever happened. They'll live in an island universe, surrounded by apparently empty space, with no way to discover the truth about cosmic history. The universe will have literally forgotten most of its own story. This isn't speculation. It's the logical consequence of accelerating expansion, combined with the finite speed of light. Information about distant regions is being erased from observability, not because it's being destroyed, but because it's moving beyond the boundary from which light can ever reach us. We're living in a special time, cosmologically, a time when the evidence of the universe's origin and evolution is still accessible. In the deep future, that evidence will be gone, lost beyond an ever-shrinking horizon. But let's return to the present and consider something even more immediate. The interstellar tunnels threading through the local bubble might not be simple structural features. They could be pathways through which material flows, conduits connecting different regions of interstellar space. Recent observations suggest these tunnels are filled with hot, low-density plasma, material heated by ancient supernova explosions that carved out the bubble in the first place. This plasma might be streaming through the tunnels, flowing from one cavity to another, creating a kind of interstellar circulation system. And here's what makes this fascinating. One of these tunnels appears to extend toward the constellation Centaurus. Another points toward Canis Major. These aren't random directions. They're aligned with specific structures in the galactic neighborhood. Could there be a tunnel extending below the solar system's plane? We don't know yet. The observations are still being analyzed, the data still being interpreted. But if such tunnels do exist in all directions, they'd represent a fundamental feature of how the interstellar medium is organized. Think of it like a cosmic highway system, not built by anyone but carved by stellar explosions, connecting different regions of space through low-density channels. Material could flow through these tunnels, traveling between bubbles more easily than through the denser surrounding medium. This matters for understanding how elements disperse through the galaxy. When massive stars explode, they scatter heavy elements into space. Those elements eventually become part of new stars and planets. But the path those elements take, the route they follow through interstellar space, depends on structures like these tunnels. The iron in your blood was created in a supernova billions of years ago, but it didn't travel in a straight line from that explosion to the cloud that eventually formed the sun. It followed the contours of the interstellar medium, possibly flowing through tunnels like the ones we're now discovering, moving through cavities and bubbles, mixing with other material along the way. You are made of stardust, yes, but you're made of stardust that took a very specific journey through galactic structure to end up here. And some of that journey might have happened through interstellar tunnels, extending in directions we're only beginning to map. Now zoom out further, beyond the local bubble, beyond the immediate interstellar neighborhood, we encounter the Orion Arm itself. This is the spiral arm of the Milky Way, where our solar system resides. A structure extending 20,000 light-years in length and 3,500 light-years in width. But the Orion Arm isn't a solid structure. It's more like a traffic jam in space, a region where stars and gas are more concentrated than in the areas between spiral arms. The spiral pattern of galaxies isn't created by material spiraling outward. It's created by density waves moving through the galactic disk, temporarily compressing material as they pass. Our solar system orbits the galactic center, completing one orbit every 225 million years. But the spiral arms rotate at a different speed. We pass through them periodically, spending some time inside an arm and some time in the less dense regions between arms. Right now, we're inside the Orion Arm, but we won't stay here forever. In a few tens of millions of years, our orbit will carry us out of this arm and into the space between spiral arms. Then, eventually, we'll enter another arm, probably Perseus or Sagittarius. Does this matter? Possibly. Some researchers have speculated that passing through spiral arms might affect Earth's climate or biology. The reasoning goes like this. Spiral arms contain more massive stars, which means more supernovae. More supernovae means more cosmic rays. More cosmic rays might affect Earth's atmosphere or cloud formation. The evidence for this is weak at best, but it's an example of how cosmic structure on galactic scales might, just barely, influence conditions on a single planet orbiting an ordinary star. When we look below the solar system toward the galactic plane, we're looking toward denser regions of the Milky Way. More stars, more gas, more dust. The galactic plane is where most of the action happens, where most stars are born and die. But we're not in the plane. We're about 55 light years above it, moving northward at 7 kilometers per second. This means we're gradually getting farther from the plane, not closer to it. This motion isn't straight up. Remember, we're also orbiting the galactic center. The combination of orbital motion and perpendicular motion creates an undulating path, like a sine wave wrapped around a circle. We bob up and down relative to the galactic plane as we orbit, crossing through it periodically. The period of this oscillation is about 70 million years. We cross the plane every 35 million years, spending half the time above it and half below. We last crossed about 3 million years ago, which means we're currently moving away from the plane, heading northward in galactic terms. In 30 million years, we'll reach maximum height above the plane, then begin falling back toward it. In 35 million years, we'll cross through the plane again, continuing to the southern side. Then the cycle repeats. This oscillation has consequences. When we're far from the plane, we're in regions of lower stellar density. Fewer nearby stars means less risk of close stellar encounters that could disrupt the Oort Cloud and send comets careening into the inner solar system. When we pass through the galactic plane, we're in denser regions, more nearby stars, higher probability of gravitational disturbances. Some researchers have suggested this might correlate with periods of increased comet impacts on Earth, possibly contributing to mass extinction events. The evidence is controversial and far from conclusive, but it illustrates how our three-dimensional motion through the galaxy exposes us to varying environments over timescales of tens of millions of years. Right now, moving away from the plane, we're in a relatively safe period. The space below us, toward the galactic plane, is more densely populated than the space above. But we're heading away from that density, into the quieter regions of the galactic halo. This motion also affects what we can observe. When we look toward the galactic plane, we're looking through more dust and gas. This obscures our view of distant objects in that direction. When we look away from the plane toward the galactic poles, we have a clearer view into intergalactic space. The South Galactic Pole lies in the constellation Sculptor. Looking in that direction, we're looking through the minimum amount of galactic material, out through what astronomers call the galaxy's south window. This makes it an ideal direction for observing distant galaxies and cosmic structures beyond the Milky Way. And this is where the story comes full circle, because when we look below the solar system toward the South Galactic Pole, we're not just looking at nearby structures. We're looking past them, through them, out into the larger universe beyond. We see the local group, the collection of galaxies including the Milky Way and Andromeda. We see the local sheet, the flattened distribution of galaxies that bounds the local void. We see that void itself, a vast region of space containing far fewer galaxies than average. And beyond that, we might be looking through the KBC Void, that controversial structure that may or may not exist, a region of underdensity 2 billion light-years across that could explain puzzling observations about the universe's expansion rate. Then, at the greatest distances, we see the cosmic web itself, the large-scale structure of the universe with its filaments and voids and sheets of galaxies, all shaped by dark matter and dark energy, all evolving according to physical laws we're still working to fully understand. The view below the solar system is a view through time and scale, from the familiar to the mysterious, from the local to the cosmic. Every direction contains layers of structure, each telling part of the story of how the universe is organized and how it came to be this way. So where does that leave us when we trace these structures into the distant universe? Every photon that reaches us from those far regions has traveled through an obstacle course of cosmic architecture. Light from distant galaxies passes through the local bubble, threading between the sparse atoms of the local interstellar cloud, crossing the boundaries where one structure gives way to another. Each passage leaves subtle fingerprints on the light itself. Astronomers use these fingerprints to map what lies between us and those distant objects. Absorption lines in spectra reveal the presence of gas clouds. The light gets dimmed by dust. Its polarization changes as it passes through magnetic fields. Every alteration tells us something about the intervening material. This matters because we're not just passive observers of a static universe. We're moving through it, and it's changing around us. Consider the local bubble again. That 1,000 light-year cavity carved by ancient supernovae isn't done expanding. The shockwaves from those explosions, millions of years old, still propagate outward through the interstellar medium. They compress gas at the bubble's edges, triggering new star formation in the regions they encounter. Nearly every nearby star-forming region lies at the local bubble's boundary, caught up in that ongoing process. We entered this bubble 5 million years ago. Before that, the solar system traveled through denser regions of the galaxy where the interstellar environment was different. More dust, more gas, higher radiation levels. The heliosphere would have been compressed by the increased external pressure, possibly allowing more cosmic rays to penetrate into the inner solar system. Some researchers have speculated this could affect Earth's climate. Cosmic rays may influence cloud formation. More cosmic rays might mean more clouds, which could cool the planet. The evidence is preliminary and controversial, but it illustrates how our galactic environment might have tangible effects on conditions here. We won't leave the local bubble for another few million years. Our trajectory carries us through it at an angle, not straight across. Eventually, we'll cross back into denser interstellar regions, and the heliosphere will compress again. The cosmic ray flux will increase. Earth's climate might respond. Life will continue adapting to conditions that, on geological timescales, are constantly shifting. This is the reality of existing in a dynamic galaxy. Nothing is static. Everything flows and changes just on timescales that dwarf human experience. The interstellar tunnels connecting the local bubble to other cavities add another layer to this picture. These aren't physical tubes in any solid sense. They're channels of lower density plasma, regions where the hot gas that fills most of the bubble can flow more easily toward neighboring structures. The tunnel towards Centaurus appears to connect us to another bubble or cavity in that direction. The one toward Canis Major links to structures in that part of the sky. These connections mean the local bubble isn't isolated. It's part of a network, a three-dimensional structure that extends throughout our region of the galaxy. Map enough of these structures, and you start to see patterns. The distribution isn't random. It reflects the history of star formation and stellar death in this part of the Orion Arm over the past 20 million years. Each bubble marks where massive stars lived fast and died young, their supernova excavating vast cavities in the interstellar medium. The Orion Arm itself provides the larger context. This minor spiral arm, 3,500 light-years wide and 20,000 light-years long, is where we find ourselves in the galactic disk, not in one of the major arms like Sagittarius or Perseus, but in a smaller structure between them, a cosmic suburb rather than downtown. The arm has structure within structure, denser regions where stars form actively, sparser regions like the local bubble where the gas has been cleared away, molecular clouds where the next generation of stars is gestating, young star clusters where formation has recently occurred, old stars drifting through it all, following their own orbits around the galactic center. Looking below the solar system in the context of the Orion Arm means looking toward the inner edge of this structure, toward the regions closer to the galactic center. The density of stars increases in that direction. So does the dust and gas that obscure our view. This is why the view toward the south galactic pole is so valuable. By looking perpendicular to the galactic plane, we minimize the amount of obscuring material in our line of sight. We're looking out through the thinnest part of the disk, through regions where stellar density drops dramatically. The south galactic pole lies in Sculptor, a constellation notable for containing very few bright stars. The brightest star visible there barely reaches third magnitude. This isn't because the region is inherently devoid of stars, but because we're looking perpendicular to the galactic disk through regions where stars are sparse. What we do see in that direction are other galaxies, thousands of them. The Sculptor Group, a collection of galaxies about 12 million light-years away. The Sculptor Dwarf, a satellite galaxy of the Milky Way, one of dozens of small galaxies that orbit our own. And beyond them, countless more distant systems stretching into the deep universe. This is the power of looking away from the galactic plane. We trade nearby stars for distant galaxies. We sacrifice the local for the cosmic, and in doing so, we gain perspective on our place in the larger universe. That perspective reveals something profound about cosmic structure. The distribution of matter isn't uniform, it's hierarchical. Stars cluster into galaxies. Galaxies cluster into groups. Groups cluster into larger structures called superclusters. And between these concentrations lie voids, vast regions where galaxies are rare. The local void is one such structure. Discovered in 1987, it spans at least 150 million light-years, possibly up to 300 million. It sits adjacent to the local group, beginning at our cosmic neighborhood's edge and extending outward into regions we're still mapping. The void isn't completely empty. A few scattered galaxies drift through it, isolated systems separated by enormous distances. But compared to the density of galaxies in the local sheet or other nearby structures, the void is remarkably underpopulated. Why? The answer lies in how structure formed in the early universe. Tiny quantum fluctuations in the density of matter present in the first moments after the Big Bang grew over billions of years through gravitational attraction. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming even more sparse. Over cosmic time, this process created the cosmic web we see today. Dense filaments, where galaxies cluster, nodes where filaments intersect, forming massive galaxy clusters, sheets or walls of galaxies marking boundaries, and voids, the regions between these structures, where matter has been gravitationally evacuated over billions of years. The local void is one such evacuated region. Matter that might have formed galaxies, there was instead pulled toward the denser regions surrounding it, toward the local sheet and the structures beyond. What remains is a vast, relatively empty bubble in the cosmic web. But here's where things get interesting. Some researchers have proposed that we might be inside an even larger void. The KBC Void, named after the astronomers who studied it in 2013, is a controversial structure. If it exists, it's enormous, roughly 2 billion light-years across, with the Milky Way near its center. The entire local group, the local sheet, even the local void would all be contained within this vast underdensity. The evidence comes from observations of the universe's expansion rate. Measurements of nearby galaxies suggest the universe is expanding faster than measurements of the cosmic microwave background indicate it should. This discrepancy, called the Hubble tension, is one of the most puzzling problems in modern cosmology. One explanation is that we're inside a large void. Matter inside a void would be less dense than average, which would affect local expansion measurements. The universe locally would appear to expand faster than it does on average because there's less matter nearby to slow the expansion through gravity. Recent studies using baryon acoustic oscillations, subtle patterns in the distribution of galaxies that act like cosmic rulers, suggest this void model might be valid. The data seems consistent with a large underdense region centered roughly on our position. But other researchers remain skeptical. The void would have to be extraordinarily large and precisely centered on us, which seems suspicious. Are we really that special? Or are we misinterpreting the data? The debate continues. More observations are needed. Better measurements of the expansion rate at various distances. Deeper surveys of galaxy distributions. Refined theoretical models of how voids affect cosmological measurements. What we can say is this: whether or not the KBC void exists, the local void definitely does. We sit at the edge of a vast underdense region, looking out into space that contains far fewer galaxies than average. Below the solar system, in the direction towards Sculptor and the South Galactic Pole, we're looking through this void, past it, toward the structures beyond. Those structures include the larger cosmic web, filaments of galaxies stretching across hundreds of millions of light years. The Laniakea Supercluster, of which the local group is a tiny part. The Great Attractor, a gravitational anomaly toward which our entire region of space is flowing. Every direction we look reveals layers of this architecture. Below the solar system is no exception. From the Oort Cloud through the local bubble, from the Orion Arm through the local void, from nearby galaxies to distant cosmic structures, each layer adds another chapter to the story of where we are and how we got here. And we're still discovering new chapters. New observations reveal unexpected structures. New theories explain patterns we hadn't understood. The picture grows more detailed with each advance in technology and understanding. Below the solar system, we're also looking through something invisible yet profound: dark matter. This mysterious substance makes up roughly 95% of our galaxy's mass, yet we can't see it, touch it, or directly detect it. We only know it exists because of its gravitational effects. The Milky Way's dark matter halo extends far beyond the visible disk, reaching out at least 300,000 light-years from the galactic center, possibly further. This halo is spherical, enveloping the entire galaxy equally in all directions. When you look below the solar system, you're looking through this vast, invisible structure. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can measure. It passes through ordinary matter without friction or resistance. The only way we detect it is through gravity, by observing how its mass affects the motion of stars and galaxies. And there's a lot of it. The dark matter in the Milky Way outweighs all the visible stars, gas and dust by a factor of roughly 20. Everything we can see, the billions of stars, the glowing nebulae, the planets, represents only about 5% of the galaxy's total mass. The rest is dark matter, forming an enormous spherical halo that dwarfs the visible disk. This has profound implications for our understanding of what lies below the solar system. The space beneath us isn't just filled with the structures we've discussed: the Oort Cloud, the Heliosphere, the local bubble. It's also permeated by dark matter, an invisible scaffolding that shapes the motion of everything within the galaxy. We don't know what dark matter is made of. Leading candidates include WIMPs, weakly interacting massive particles, or axions, hypothetical particles far lighter than electrons. Experiments around the world are searching for these particles, but so far, none have been definitively detected. What we do know is that dark matter was crucial to the formation of galaxies. In the early universe, dark matter's gravity pulled ordinary matter together, creating the conditions for stars and galaxies to form. Without dark matter, the universe would look completely different. Galaxies might not exist at all. This invisible component of the cosmos surrounds us constantly. Dark matter particles could be passing through your body right now, billions of them every second, completely undetected. They interact so weakly with ordinary matter that they pass through the entire Earth without stopping. Looking below the solar system means looking through this dark matter halo, through a substance that dominates the galaxy's mass, but remains fundamentally mysterious. The solar system is also moving through the galaxy in a way that connects to what lies below us. We're not just orbiting the galactic center in a flat circle. We're oscillating up and down, bobbing above and below the galactic plane like a horse on a carousel. This oscillation has a period of roughly 70 million years. We cross through the galactic plane every 35 million years. Currently, we're positioned about 55 light-years above the plane and moving northward, away from it. We last crossed the galactic plane about 3 million years ago. We won't cross it again for another 30 million years. This motion affects what we encounter. When we're above the plane, we're in a region of lower stellar density, fewer molecular clouds, less dust. When we cross through the plane, we pass through denser regions where star formation is more active. Some scientists have speculated that this oscillation might influence life on Earth. The hypothesis suggests that passing through the galactic plane exposes us to more cosmic rays, potentially increasing mutation rates or triggering climate changes. The evidence for this is controversial and far from conclusive, but it's an intriguing idea that our vertical motion through the galaxy might leave traces in Earth's geological and biological record. What this means for understanding what lies below the solar system is that below changes over cosmic timescales. Right now, below means away from the galactic plane towards sparser regions. In 30 million years, below will mean toward the galactic plane, toward denser regions filled with more stars and gas. The galaxy itself is a dynamic structure. The spiral arms rotate. Stars orbit at different speeds depending on their distance from the center. The disk warps and flexes under gravitational influences. Nothing is static, and we're part of this motion. The solar system is a tiny speck moving through vast galactic currents, oscillating through the plane, orbiting the center, all while the galaxy itself rotates and evolves. Below the solar system right now lies a path we've traveled before and will travel again. The space beneath us has witnessed countless crossings as the sun completes its galactic orbit, each time bringing us through different regions, different environments, different cosmic neighborhoods. There's also the question of what lies beyond our galaxy. When we look below the solar system toward the south galactic pole, toward the constellation Sculptor, we're looking out what astronomers call the galaxy's south window. Stellar density is extremely low in this direction. Very few bright stars obstruct the view. This makes it an ideal observing direction for studying structures beyond the Milky Way. And there are structures, lots of them. The local group, our collection of galaxies, extends in 3 dimensions around us. Some of these galaxies lie in directions we'd consider below the solar system. The small Magellanic Cloud, for instance, is visible from the southern hemisphere. It's a dwarf galaxy orbiting the Milky Way, about 200,000 light-years away. The local group is part of the larger Laniakea Supercluster, a vast collection of galaxies spanning 520 million light-years. This supercluster contains roughly 100,000 galaxies, including the Milky Way, Andromeda, and the Virgo cluster. Laniakea itself is part of an even larger structure, the cosmic web. This web is the largest known structure in the universe, a network of galaxy filaments separated by vast voids. Looking below the solar system takes us through layers of this hierarchy, from the Oort Cloud through the local bubble, from the Orion Arm through the local void, from the local group through Laniakea. Each layer connects to the next, revealing the nested structure of cosmic organization. The cosmic web formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter through gravity, growing over billions of years into the filaments and clusters we see today. The voids formed where matter was pulled away, evacuated by the gravitational attraction of denser regions. What remains are vast empty spaces, the largest structures in the universe by volume, though they contain very little mass. This web extends in all directions, including below the solar system. The filaments, the voids, the clusters, they surround us completely, forming the large-scale structure of the universe. Recent observations have revealed something unexpected about this structure. The local bubble, that cavity carved by ancient supernovae, appears to be connected to other bubbles through interstellar tunnels. These tunnels are channels of hot, low-density plasma that punch through the denser surrounding material. They connect different cavities in the interstellar medium, creating a network of passages through space. One tunnel appears to stretch toward the constellation Centaurus. Another seems to link toward Canis Major. These features were detected through careful mapping of the interstellar medium's temperature and density. The tunnels formed when expanding supernova remnants encountered each other. Where two bubbles met, they merged, creating passageways between them. Over time, these passages have evolved into the tunnel structures we observe today. This means the local bubble isn't isolated. It's part of a larger network, connected to other cavities through these interstellar passages. And these tunnels likely extend in multiple directions, possibly including pathways that reach below the solar system's plane. The structure resembles a sponge, holes and tunnels, cavities and passages, all carved by stellar explosions and strong stellar winds. The interstellar medium isn't uniform. It's a complex, three-dimensional structure shaped by violent events over millions of years. We're inside one cavity of this sponge, looking out through tunnels toward other cavities. The space below the solar system includes portions of this network. These passages carved through the interstellar medium by ancient cosmic violence. There's something almost surreal about this. We tend to think of space as empty, as a void to be crossed. But space has structure. It has architecture. The interstellar medium is carved into chambers and passages, shaped by forces operating over scales we can barely comprehend. And we're moving through it. The solar system entered the local bubble about 5 million years ago. Before that, we were in denser regions of the interstellar medium. Eventually, we'll exit the bubble and enter new regions with different properties. This motion through the galaxy exposes us to different environments over time. Sometimes we're in bubbles, sometimes in denser clouds, sometimes we're near star-forming regions, sometimes in quieter neighborhoods. The journey continues, the environment changes, and the solar system adapts to each new setting. What lies below the solar system is also changing as we move. The structures we observe today will shift as our perspective changes. New regions will come into view. Others will recede behind us. The cosmic landscape continuously evolves around our moving vantage point. There's also the magnetic field threading through all of this. The interstellar medium isn't just gas and dust, it's magnetized, with weak magnetic fields extending throughout the galaxy. These fields are generated by the motion of charged particles, primarily by the rotation of the galaxy itself and by stellar activity. They thread through space in complex patterns, influencing the motion of charged particles and shaping the structure of the interstellar medium. The Local Interstellar Cloud, that denser region within the local bubble where the solar system currently resides, has its own magnetic field. This field interacts with the Sun's magnetic field at the heliopause, creating a complex boundary layer where solar and interstellar magnetism meet. Voyager 2, traveling southward below the plane of the planets, is exploring this boundary region. Its instruments measure the strength and direction of magnetic fields, revealing how they change as the spacecraft moves through different regions of space. These measurements have shown that the transition from the heliosphere to interstellar space isn't sharp. It's a boundary layer where fields and particles mix, where solar influence gradually gives way to interstellar conditions. The magnetic fields extend in all directions, including below the solar system. They're part of the invisible architecture of space, shaping the flow of cosmic rays and influencing the structure of the interstellar medium. Below the solar system lies a tapestry of structures, visible and invisible, matter and energy, fields and forces. From icy comets in the Oort Cloud to dark matter halos, from supernova-carved bubbles to magnetic field lines, each component adds another thread to the cosmic fabric. And we're still discovering new threads. Technology improves. Observations reveal unexpected patterns. Theories evolve to explain what we find. The picture of what lies below the solar system grows more detailed with each advance. Yet each answer raises new questions about the nature of space and our place within it. And all of this exists within an even larger framework, one that becomes visible when we pull back further and look at how galaxies themselves are distributed in space. The local group, that collection of galaxies including the Milky Way and Andromeda, isn't floating in isolation. It's part of a flattened structure called the local sheet. This arrangement surprised astronomers when they mapped it. Galaxies don't cluster randomly in 3 dimensions. They prefer to gather in sheets and filaments, leaving vast voids between them. The local sheet extends in a plane roughly perpendicular to our line of sight when we look toward the constellation Virgo. It's about 7 million light-years thick, but stretches much farther in the other 2 dimensions. The Milky Way sits within this sheet, along with dozens of other galaxies, all moving through space together in a loose association. What makes this relevant to what lies below the solar system is geometry. The local sheet has an orientation in space. Looking in certain directions takes us through the thickness of the sheet. Looking in other directions follows along its length. When we look southward from the solar system, below the plane of the planets, we're looking at an angle to this larger structure. The sheet itself borders something remarkable: the local void. This region of space contains far fewer galaxies than average. It stretches at least 150 million light-years across, possibly much farther. Astronomers discovered it in 1987, but its exact boundaries remained uncertain for decades. Recent mapping efforts have revealed it consists of 3 separate sectors connected by thin bridges of galaxies. The void isn't completely empty. Scattered galaxies exist within it, but their density is significantly lower than in surrounding regions. It's like comparing a sparsely populated rural area to a dense city. Both contain inhabitants, but the distribution differs dramatically. Why does this matter? Because the gravitational influence of this underdense region affects the motion of nearby galaxies, including our own. The void repels, while denser regions attract. The Milky Way is being pulled toward the Virgo cluster and other concentrations of mass, while simultaneously being pushed away from the local void. These competing influences shape our path through the universe. Some researchers have proposed an even larger structure, the KBC Void, named after the astronomers who studied it. This proposed underdensity would be truly enormous, roughly 2 billion light-years across. If it exists, the Milky Way would sit near its center, surrounded in all directions by a region of lower than average galaxy density. The evidence remains debated. Some measurements suggest we do inhabit such a void. Others question whether the apparent underdensity is real or an artifact of how we measure cosmic distances. The debate connects to one of cosmology's persistent puzzles, the Hubble tension, a discrepancy between different measurements of how fast the universe is expanding. If the KBC Void is real, it would explain some of these measurement differences. Local observations would give slightly different results than measurements from the distant universe, because we'd be observing from inside an unusual region. Recent studies using baryon acoustic oscillations, ripples in the distribution of galaxies left over from the early universe, suggest the void model might be valid. These structures exist in 3 dimensions around us. Looking below the solar system takes us through the local sheet at a particular angle, toward or through portions of the local void, with the KBC Void potentially encompassing everything. The cosmic geography is complex, layered, and still being mapped. Meanwhile, the distribution of dark matter adds another dimension to this picture. The dark matter halo surrounding the Milky Way extends far beyond the visible galaxy. Current estimates suggest it reaches at least 300,000 light-years from the galactic center, possibly farther. This halo is roughly spherical, meaning it extends equally in all directions, including below the solar system. Dark matter doesn't cluster into stars or planets. It interacts primarily through gravity, shaping the large-scale structure of the universe without producing light. The halo around the Milky Way contains perhaps 20 times more mass than all the visible matter in the galaxy combined. It's the gravitational anchor that holds everything together. When we look below the solar system, we're looking through this dark matter halo. We can't see it directly, but we can infer its presence from its gravitational effects. It influences the motion of stars in the outer reaches of the galaxy. It affects how satellite galaxies orbit the Milky Way. It shapes the distribution of gas in the galactic halo. The dark matter also extends beyond individual galaxies. The local group has its own dark matter distribution, distinct from the halos of individual galaxies. On even larger scales, clusters of galaxies sit within their own enormous dark matter concentrations. The cosmic web, that network of filaments and sheets connecting galaxy clusters, is fundamentally a dark matter structure. Visible galaxies simply trace where the dark matter is concentrated. This invisible scaffolding exists throughout space. Looking in any direction, including below the solar system, takes us through regions dominated by dark matter. It's the majority component of the universe by mass, yet it remains mysterious. We know it exists, we can map its distribution, but we don't know what it's made of. The search continues. Detectors buried deep underground wait for the rare collision between a dark matter particle and ordinary matter. Telescopes map gravitational lensing effects that reveal dark matter concentrations. Particle accelerators search for hints of new physics that might explain dark matter's nature. Each approach offers a different perspective on the same fundamental question. While this search proceeds, we can still map where dark matter concentrates and how it shapes cosmic structure. The Milky Way's dark halo, the local group's dark matter distribution, the dark matter filaments connecting galaxy clusters. All of these extend through the regions below the solar system. They form an invisible landscape, as real as the visible one, detected through gravity's subtle effects. Consider also the cosmic microwave background radiation that permeates all of space. This ancient light, released when the universe was only 380,000 years old, travels through space in all directions. Photons from this primordial glow pass through the region below the solar system, just as they do everywhere else. They've been traveling for nearly 14 billion years, stretched to microwave wavelengths by the expansion of space. These photons carry information about the early universe. Their temperature varies slightly across the sky, tiny fluctuations that reveal the density variations from which all structure grew. These variations existed when the universe was remarkably uniform, before gravity had time to amplify small differences into the clusters and voids we see today. The cosmic microwave background provides a backdrop against which all other structures exist. It's the oldest light we can observe, a snapshot of the universe in its infancy. When astronomers study distant galaxies, they're looking at light that has traveled across space through the cosmic microwave background to reach us. This ancient radiation fills space uniformly, including the regions below the solar system. Another pervasive feature is cosmic rays, high-energy particles that stream through space. They originate from various sources: supernova remnants, active galactic nuclei, perhaps even more exotic phenomena. These particles travel near light speed, their paths bent by magnetic fields, but generally moving in straight lines through the tenuous interstellar medium. Cosmic rays arrive at Earth from all directions. They don't prefer any particular orientation. Some come from above, some from below, some from the sides. They're a constant rain of high-energy particles that has persisted throughout the history of the solar system. Earth's magnetic field deflects many of them, and the atmosphere absorbs most of those that make it through. But they're always there, part of the environment we inhabit. These particles interact with the interstellar medium as they travel. They ionize atoms, influence chemical reactions, and contribute to the heating of interstellar gas. They're another invisible but omnipresent component of the space between stars, existing equally in all directions around us. The solar system's motion through the galaxy carries us through all of these environments. We're currently moving northward away from the galactic plane at about 7 kilometers per second. This means the galactic plane itself lies in the direction we consider below the solar system. Eventually, our oscillating path will carry us back toward the plane. In about 30 million years, we'll cross through it again, entering the denser regions of the galactic disk. This oscillation has consequences. When we're far from the plane, we encounter fewer molecular clouds and less interstellar dust. The environment is quieter, less dynamic. When we pass through the plane, we move through denser regions where star formation is active and supernova more frequent. The cosmic weather changes with our position. Some researchers have speculated that these passages through the plane might correlate with events on Earth: mass extinctions, climate changes, geological activity. The evidence remains debated. The gravitational effects of passing through the denser regions of the disk are subtle. The increase in cosmic ray exposure is real but modest. Whether these influences are strong enough to affect life on Earth remains an open question. What's certain is that our galactic environment changes over time. The view below the solar system will look different 30 million years from now when we cross the galactic plane. Different star fields will be visible. Different molecular clouds will dot the landscape. The journey continues and the scenery evolves. This brings us back to a fundamental realization. Space is not static. It's dynamic, evolving, constantly changing. The structures we observe below the solar system are snapshots of ongoing processes. Bubbles expand, clouds drift, galaxies move, voids grow. Everything is in motion, shaped by gravity and pressure, and magnetic fields over timescales that dwarf human experience. The picture of what lies below the solar system is now more complete. From the icy bodies of the Oort Cloud to the protective Heliosphere, from the Local Interstellar Cloud to the supernova-carved local bubble, from magnetic field lines to dark matter halos, from the local sheet to the local void, each layer reveals another aspect of cosmic structure. And beyond all of this, the cosmic microwave background and the larger framework of cosmic expansion provide context for everything we observe. We are travelers in a cosmic ocean that never stops moving. Every structure below the solar system, the Oort Cloud, the Heliosphere, the Local Interstellar Cloud, the supernova-carved local bubble, exists within this dynamic framework. Nothing holds still. The interstellar medium flows past us at 7 kilometers per second. The local bubble continues expanding from those ancient explosions. Magnetic field lines bend and twist under invisible pressures. Dark matter, that mysterious scaffolding of the cosmos, permeates everything in densities we can measure but barely understand. And threading through all of this are those interstellar tunnels connecting the local bubble to other cavities. Channels of hot, low-density plasma punching through denser regions like cosmic highways. One tunnel appears to stretch toward Centaurus. Another reaches toward Canis Major. These aren't rigid structures. They're more like temporary pathways carved by the pressure of stellar winds and supernova shockwaves, maintained by ongoing processes we're only beginning to map. The tunnels likely extend in multiple directions from our location. Some may reach toward regions below the solar system's plane. Others connect to bubbles and cavities we haven't yet discovered. The local bubble isn't isolated. It's part of a larger network, a cosmic foam of interconnected voids and filaments, shaped by stellar violence over millions of years. This foam structure extends throughout the Orion Arm, the minor spiral arm where our solar system resides. The Orion Arm itself spans 3,500 light-years in width and extends roughly 20,000 light-years in length. We're positioned about halfway along its length, riding this galactic wave through space. The arm exists in 3 dimensions, curving both above and below the galactic plane as it spirals outward from the galaxy's center. When we look below the solar system, we're looking through this spiral arm structure toward the galactic plane. The arm doesn't block our view so much as color it. Stars in the arm provide foreground objects. Gas and dust in the arm scatter light from more distant sources. The arm shapes what we can observe, filtering our perception of deeper space. But the Orion Arm is temporary, not in human timescales, but in galactic ones. Spiral arms aren't solid structures. They're density waves, regions where stars and gas temporarily bunch together before moving on. Individual stars orbit the galaxy at different speeds. They enter spiral arms, spend time in the denser environment, then exit on the other side. The arms persist because new stars keep entering as old ones leave. Our solar system has passed through multiple spiral arms during its 4.6 billion-year journey around the galaxy. We've been in the Orion Arm for several million years. Eventually, we'll exit into the space between arms, entering a less dense region where star formation is quieter and supernova less frequent. The cosmic weather will change again. This brings us to something profound about directionality in space. When we talk about below the solar system, we're imposing human categories onto a structure that doesn't inherently have up or down. The ecliptic plane of the solar system provides one frame of reference. The galactic plane offers another. The cosmic microwave background suggests a third, the reference frame in which the CMB appears most uniform, which astronomers call the CMB rest frame. None of these frames is more correct than the others. They're tools for organizing our observations. The solar system's ecliptic makes sense for studying planets. The galactic plane helps us understand our position in the Milky Way. The CMB rest frame reveals our motion through the larger universe. What actually exists below the solar system depends on which frame you choose. Below the ecliptic, we find the same structures that exist above: the spherical Oort Cloud, the protective heliosphere, the surrounding interstellar medium. Below the galactic plane, we encounter the denser disk regions, the molecular clouds, the active star-forming areas. These are distinct regions with different properties. The solar system's tilt relative to the galactic plane, that 60-degree angle, creates this complexity. We're sailing through the galaxy sideways, as one researcher put it. Our ecliptic doesn't align with the galactic disk. Our north doesn't match the galaxy's north. This misalignment means our journey cuts across galactic structures at unexpected angles, and we're currently above the galactic plane, moving farther north at 7 kilometers per second. This northward motion carries us away from the densest concentrations of matter in the galactic disk. The environment around us becomes gradually less dense. Fewer molecular clouds, less dust, a quieter cosmic neighborhood. But this is temporary. Gravity pulls us back. Every star in the galaxy experiences this same force, drawing objects toward the galactic plane when they drift too far away. We'll reach a maximum distance north. Perhaps we're already near it, then begin falling back toward the plane. In 30 million years, we'll cross through the disk again, entering the denser southern regions. This oscillation has happened dozens of times during the solar system's history. Each crossing brings us through different regions of the galaxy, different molecular clouds, different star clusters, different radiation environments. The cosmic scenery changes with each passage. Some researchers have proposed that these passages through the galactic plane might trigger events on Earth. The reasoning goes like this. Denser regions contain more matter. More matter means stronger gravitational perturbations on the Oort Cloud. More perturbations mean more comets get knocked into the inner solar system. More comets mean higher impact rates on Earth. The evidence for this connection remains debated. Impact craters on Earth do show clustering in time. Some mass extinction events might correlate with predicted plane crossings, but the signal is noisy. Other factors complicate the picture. The hypothesis is plausible but not proven. What we know with certainty is that our galactic environment changes over time. the structures below the solar system today won't be the same structures below it 30 million years from now. We'll be in a different part of the galaxy. Different stars will be nearby. Different clouds will surround us. The journey continues, and the cosmic landscape evolves. This dynamic picture extends to the largest scales. The local group of galaxies, which includes the Milky Way and Andromeda, along with dozens of smaller galaxies, is itself moving through space. The local group is falling toward the Virgo cluster at 600 kilometers per second. Beyond that, we're part of a larger structure called Laniakea, a supercluster of galaxies being pulled toward an even more massive concentration of matter called the Great Attractor. These motions happen in 3 dimensions. Some galaxies in the local group would be positioned in directions we consider below the solar system. As these galaxies move, as the local group evolves, as galaxies merge and new structures form, the view in every direction changes. Space is not a static backdrop. It's an active, evolving environment. And all of this motion happens against the background of cosmic expansion. Space itself continues stretching, carrying distant galaxies away from us at speeds that increase with distance. The most remote galaxies recede faster than light, not because they're moving through space that quickly, but because the space between us and them is expanding so rapidly. This expansion doesn't affect structures held together by gravity. The solar system won't expand. The Milky Way won't expand. Even the local group remains bound. But on larger scales, beyond the local group, beyond Laniakea, expansion dominates. The universe grows, carrying galaxy clusters apart, creating more space between structures. That expanding space exists below the solar system, just as it exists in every other direction. When we look at distant galaxies in the southern sky, we're observing objects being carried away by cosmic expansion. Their light reaches us redshifted, stretched to longer wavelengths by the expansion of space itself. The farther the galaxy, the greater the redshift. The greater the redshift, the faster the recession. Eventually, we reach distances where galaxies recede so rapidly that their light will never reach us. A cosmic horizon, a boundary beyond which we cannot see. This horizon exists equally in all directions. Below the solar system, above it, in every direction we look, there are regions of space that remain forever beyond our observation, not because those regions don't exist. They're out there, filled with galaxies and stars and probably planets. But the expansion of space has carried them so far away and continues carrying them so rapidly that even light traveling at cosmic speed limits cannot bridge the growing gap. They've slipped beyond our observable universe. The observable universe has a radius of about 46 billion light years. That's how far light has been able to travel toward us during the 13.8 billion years since the Big Bang, accounting for the expansion of space during that time. Everything within that sphere is potentially observable. Everything beyond it is not. This sphere is centered on us, not because we're special, but because observable universe is an observer-dependent concept. An observer in a distant galaxy would see a different observable universe centered on them with its own 46 billion light-year radius. Their observable universe would overlap with ours in some regions and extend into areas we can never see. The structures below our solar system then extend far beyond what we can observe. The Local Interstellar Cloud gives way to the local bubble. The local bubble connects to other bubbles and cavities through interstellar tunnels. Those structures exist within the Orion Arm. The Orion Arm spirals through the Milky Way. The Milky Way sits in the Local Group. The Local Group inhabits a sheet-like structure bordering the Local Void, and beyond that, larger structures extend to the limits of observation and beyond. Each layer reveals new patterns, new organizing principles, new scales of structure. From the icy bodies of the Oort Cloud to the cosmic horizon, from the solar wind to the cosmic web, matter arranges itself in hierarchies shaped by gravity, pressure, magnetic fields, and the fundamental forces of nature. We observe these structures from a single location, a small rocky planet orbiting an ordinary star in an unremarkable spiral arm of a typical spiral galaxy. But that single vantage point has revealed an astonishing amount about the universe's architecture. Every photon that reaches our telescopes carries information about distant structures. Every measurement adds another piece to the cosmic puzzle. The picture is incomplete. Dark matter remains mysterious. Dark energy defies easy explanation. The precise shape and extent of many structures remain uncertain. The interstellar tunnels might connect in ways we haven't mapped. The local void might be part of something larger. The oscillation through the galactic plane might have effects we haven't detected, but the framework is solid. We understand the basic architecture. We know the major structures. We can trace our location through multiple frames of reference, from local to cosmic scales. The view below the solar system is no longer a mystery. It's a map, constantly being refined, revealing the dynamic, interconnected nature of the cosmos we inhabit. The journey from our Oort Cloud to the cosmic horizon reveals something fundamental about existence itself. We're not observers standing outside the universe, looking at it objectively. We're embedded within it, moving through structures that dwarf comprehension, surrounded by forces we detect but barely understand. Below the solar system isn't a destination. It's a direction through cosmic architecture that exists equally in every orientation. The spherical Oort Cloud surrounds us completely. The Heliosphere extends in all directions. The Local Interstellar Cloud has no preferred axis. Dark matter permeates space uniformly. The cosmic microwave background bathes everything in ancient light from every angle. What changes with direction is what we observe. Looking below the ecliptic plane takes us through the same local structures but toward different distant objects. Looking toward the South Galactic Pole provides clearer views into intergalactic space because we're looking perpendicular to the dusty galactic disk. Looking toward Sculptor takes us through regions of low stellar density, through the local void, toward cosmic structures billions of light years away. These aren't separate places, they're nested layers of a single interconnected reality. The Oort Cloud exists within the Heliosphere. The Heliosphere exists within the Local Interstellar Cloud. The Local Interstellar Cloud exists within the local bubble. The local bubble exists within the Orion Arm. The Orion Arm exists within the Milky Way. The Milky Way exists within the local group. The local group exists within the local sheet. The local sheet borders the local void. And all of this exists within the larger cosmic web shaped by dark matter and driven by dark energy. Each layer influences the others. The heliosphere protects us from the local interstellar cloud. The local bubble's low density affects how cosmic rays propagate. The Orion Arm structure shapes our view of distant galaxies. The Milky Way's dark matter halo holds everything together gravitationally. the local void's underdensity influences the motion of nearby galaxy groups. Dark energy drives the expansion that ultimately determines cosmic fate. We're traveling through these structures at multiple speeds simultaneously, 7 kilometers per second northward away from the galactic plane, 25 kilometers per second toward the constellation Leo as the solar system orbits the galactic center, 600 kilometers per second toward the Virgo cluster as the local group falls through space. And underlying all of this, the expansion of space itself carries distant structures away at velocities that increase with distance. These motions aren't random. They're responses to gravitational forces operating across vast scales. The galactic plane pulls us back when we drift too far north. The galactic center holds us in orbit through its immense mass. The Virgo cluster attracts through the combined gravity of thousands of galaxies. Dark matter halos shape these motions through invisible gravitational scaffolding. Dark energy counters gravity on the largest scales, driving acceleration that will ultimately separate galaxy clusters beyond the possibility of interaction. What lies below the solar system, then, depends on timescale. Right now, we're looking through relatively sparse regions toward the galactic plane and beyond. In 30 million years, we'll be crossing through that plane, surrounded by denser molecular clouds and more active star formation regions. In 200 million years, we'll complete another orbit around the galaxy, having passed through different spiral arms and encountered different interstellar environments. In billions of years, the Milky Way will merge with Andromeda, fundamentally reshaping the cosmic neighborhood. The structures themselves evolve. The local bubble continues expanding from those ancient supernova explosions. New bubbles form where massive stars explode today. Interstellar tunnels shift as pressure distributions change. Molecular clouds drift and collide, triggering new episodes of star formation. The galactic spiral pattern rotates at its own pace, independent of the stars within it. Galaxies merge, creating new structures from old ones. And through all of this, we're observers becoming aware of our own cosmic context. Every photon that reaches our telescopes traveled through these structures. Every measurement we make samples the environment at a specific location and time. Every theory we develop attempts to explain patterns in data filtered through our position in space and our moment in cosmic history. The view below the solar system is our view from here, now. An observer in another galaxy would see different structures, different voids, different filaments. An observer, 1 billion years in the future, would see the same regions evolved, changed by processes operating over geological timescales. An observer at the edge of the observable universe would see cosmic structures we can never observe, beyond our horizon, forever disconnected from our causal sphere. But from our perspective, the picture is remarkable. We've traced our cosmic address from the Oort Cloud to the cosmic web. We've identified the structures that surround us, the forces that shape them, the processes that drive their evolution. We've mapped dark matter halos we cannot see. We've detected dark energy through its effects on cosmic expansion. We've peered through interstellar bubbles toward distant voids and clusters. The space below the solar system contains the same fundamental components as space in any other direction. Ordinary matter forming stars and gas clouds. Dark matter providing gravitational structure. Dark energy driving accelerated expansion. Magnetic fields threading through the interstellar medium. Cosmic rays streaming from distant sources. the cosmic microwave background carrying information from the early universe. What varies is the specific arrangement. The particular stars, clouds, galaxies, and voids visible in each direction. The density of the interstellar medium along different lines of sight. The amount of obscuring dust between us and distant objects. The gravitational influences from nearby massive structures. These variations matter for what we can observe. Looking toward the galactic pole provides clearer views than looking through the galactic plane. Looking away from the local void reveals more galaxies than looking toward it. Looking in the direction of our motion through space shows different redshifts than looking opposite that motion, but the underlying reality remains the same. Space extends in all directions. Structures exist at multiple scales. Forces operate according to physical laws. Matter and energy interact through fundamental principles. The universe is comprehensible, even when individual components remain mysterious. Dark matter's identity remains unknown. Dark energy's nature defies easy explanation. The precise mechanisms of galaxy formation continue to puzzle researchers. The exact shape of interstellar tunnels awaits better mapping. The question of whether we're inside a supervoid remains debated, yet we know enough to understand the broad picture. Matter clumps under gravity. Stellar explosions carve bubbles. Magnetic fields thread through plasma. Galaxies cluster along filaments. Voids mark regions where matter has been gravitationally evacuated. The cosmic web reflects the growth of structure from tiny quantum fluctuations in the early universe. These aren't abstract concepts disconnected from daily experience. We're made of atoms forged in ancient stars. The iron in our blood came from supernova explosions. The calcium in our bones was created in stellar cores. The oxygen we breathe was synthesized through nuclear fusion. The water we drink contains hydrogen from the Big Bang itself. We're not separate from cosmic structures, we're part of them. Temporary arrangements of matter that have achieved self-awareness, capable of studying the universe that created us. Every observation we make, every measurement we take, every theory we develop represents the universe examining itself through evolved consciousness. Looking below the solar system is really the universe looking at itself from one particular angle, through one particular set of structures, at one particular moment in cosmic time. The view reveals layers of organization from local to cosmic scales, from the familiar to the mysterious, from the observed to the inferred, and the exploration continues. New telescopes probe deeper into space and further back in time. Improved detectors search for dark matter particles. Better instruments map the interstellar medium in greater detail. Refined theories attempt to explain dark energy's nature. Each advance brings new insights and new questions. The structures below the solar system aren't static museum pieces to be catalogued and forgotten. They're active, evolving features of a dynamic cosmos. They shape our environment. They influence what we can observe. They provide context for understanding our place in the universe. They challenge us to comprehend scales and forces far beyond everyday experience. From the Oort Cloud's icy wanderers to the cosmic horizon's unreachable galaxies, from the Heliosphere's protective bubble to dark energy's mysterious influence, the space below the solar system contains multitudes, nested structures, hidden forces, visible matter and invisible scaffolding, ancient light and ongoing evolution. We're travelers in this cosmic ocean, riding currents we're only beginning to map. The journey continues through structures that dwarf human timescales. The scenery changes as we move. New regions come into view while others recede behind us. The cosmic landscape unfolds according to physical laws operating across billions of years and billions of light years. What lies below the solar system is ultimately the same thing that lies in every direction. The universe itself, in all its scale and complexity, revealing patterns that connect the smallest particles to the largest structures, showing us that reality is far stranger and more magnificent than our ancestors imagined when they first looked up at the night sky and wondered what lay beyond.